Hello, my name is Daniel. I work at NXP Semiconductors. I'm part of the Linux BSD team. So my experience is mainly with the Linux kernel. And for this presentation, I will tell you my thoughts and my perspective when working with Zephyr kernel, with Zephyr OS, on adding support for a new board. So the presentation is structured like this. We will discuss about some goals that we want to achieve during this presentation and some things to get out of this room. Then we'll have a short introduction into how Zephyr development environment works, which is the Zephyr release cycle, and how to get started with Zephyr development, like getting the toolchain. Then you will have a short look on the new hardware module that was recently introduced, which is named hardware module version 2. Yeah. And then I'll share my experience coming from the Linux kernel community and my experience with this new community, with Zephyr community. So let's get started. This presentation comes as a guidance for newcomers. And what are the initial steps you need to take in order to get started with Zephyr? Then provide a short insights into the process of adding a new board. From my perspective, this version 2 model is very straightforward on what you actually need to do to have your basic support in. Then about the community collaboration, we'll get start with how you do your first contribution and what are the iterations that you need to do so that you can finally celebrate your patch acceptance. So let's get started with the Zephyr release cycle. This is pretty similar with what Linux kernel has, with some differences. First difference is, and it's quite a shock coming from Linux kernel, it's that you're no longer sending patches over email and using GitHub. Right. The release phase is, the release takes two phases. One is the development phase where actually code gets merged, work is done, there are a lot of talks there around your pull request. This takes up to 3 months, and then at some point, development stops and people are starting to test the code really well. Of course, there will be bugs, and there will be a period of 1 month when community needs to fix the bugs. This is in a series of 3 release candidates. And after this month passes, the stable release is out. Now, there are 2 parts of the maintenance things. For the periodic releases, we send updates, bug fixes, and security fixes for at least 2 cycles. And for the long-term support, every 2 years, we mark a release as supported for long-term, and we support that release for 2.5 years. Now, here is a short graph of how things happen. So, for example, after 3.5 is out, the merge windows opens for the next release. All the development happens on the main branch. Then there is this period for development, which takes 3 months, and then we get the first release candidate. At this point, after 3 months, we branch out with a new release, which will be 3.6, and we add a tag to that release so that people can build a binary and put that to test. After 3 iterations like this, the stable is out, and we restart the cycle with a new release. There is no next branch like the Linux kernel has. So in the stabilization phase, most likely you will want to stop the development for new feature and concentrate on bug fixes. Now, what you need to do in order to have a simple application compiled, you will first need the toolchain. Fortunately, Zephyr SDK supports most of the architectures and most of the operating system, important operating systems like Linux, Mac, and Windows. And you will have hosts for x86 and ARM64. And targets are listed on the right and have the important architecture already supported. So most likely when you start adding support for a new board, your toolchain will already be there. Now there is an exception, and that's the Extensa architecture, which I will base my example on. Because when integrating a CPU from Extensa, part of the CPU configuration will come via the toolchain. So for each integration, you will need to create a new toolchain. And you see here, we support lots of integration of Extensa, mostly as a result of the sound open firmware application that runs on Extensa DSPs. And you see here the vendors from MediaTek, Intel, and i.MX from NXP. But that's not really an issue. Adding support for a toolchain, it's quite easy. The important aspect here is that it takes some time. So if you look at the date of the commit here on August 21st, and we'll look at the date when this commit actually gets merged, you'll see that 1 month has passed, right? So you need to allocate on your project at least 1 month for the toolchain to get merged. The actual support for the toolchain, we use the cross tool toolchain generator, and you need to create a config file where you add some definitions there for example, the name of the toolchains and some flags. And then another important thing is that you want to add this toolchain in the CI so that the CI will generate the binaries for you. Once everything is there, hopefully your toolchain gets merged. And we calculated that if you look at the date of this release is on 1 month later, right? And once you have this toolchain, you can start working on your actual board support. Now let's have a look at the board support. And as an example for the board support, we will have a look at the i.MX plus AVK, which comes with a lot of cores that you want to work on. And actually, all the cores that are here are supported with Zephyr. You build a binary for each of the cores, and of course, each one is dedicated to a specific application. And we have these A53, M7, and the Hi-Fi 4 audio DSP here. Now let's look at the building blocks. As you can see here, we have the main CPU with the Cortex. We have the secondary cores with the M7 and the DSP. And the rest are just IPs that are on the SoC, like the audio interfaces, I don't know, PDM, DMAs, and everything one needs to have an actual non-trivial application there, and some peripherals. And we simplify this furthermore by showing the evaluation kit that has a SOC and the peripherals. And the basic goal of the presentation is to create and see the steps in order to create a minimal application that runs on the Hi-Fi 4 DSP. And the minimal application that everyone, I think, might know is the Hello World sample. That actually prints Hello World on the serial console. And in order to get this enabled, you need to have the CPU support, the UART driver, the pin control, the muxing of the pins, and some clocks, right? And let's see. With this hardware in mind, let's see what we can do. First, some things about this hardware module V2. We added support for all these CPUs before hardware module V2, and that felt very unnatural because everything was scattered around Zephyr directory hierarchy. And with this version 2, everything falls in place very natural. And this is one of the reasons it was introduced to support asymmetric multiprocessor, like SoC having different types of cores. Now, the hardware is modeled inside Zephyr into layers. And when trying to add support for a board, you look at each layer and see if the support is already there. If not, then there is work for you to implement it. The layers, we will see later a picture with all the layers, but main layers are the architecture type, the CPU, the SoC family we'll see later, and the board part. This model version 2 is in the current release, current working releases, which is 3.7. And from my experience, I'm not sure if that's true or not. Adding support for a board is like 80% writing configuration files and 20% actual C code, right? Support for specific stuff there. At first, it might be very confusing, and you might get a lot of trouble understanding what kconfig file do you want to add, where to add the DTS and stuff like that. But as usual, and as always in open source development, you just try to find a board that's similar with yours and follow that example. And another trick that I always follow is I look inside the history, inside Git history, and see the steps and how the commits were arranged in order to introduce the board. That's a very good example. If you find a board that does this, then you are mostly saved, right? Now, before going to details, we have some terminology that will be used across this presentation. And actually, what is a board? We call a board the target system that can actually load and execute the application image. Now, the board target is the full string used to compile an image for a particular hardware. You will see that for a board, we can have multiple board targets. Now, the board name is just a tiny part that we identify in a human-readable way, the board. And the board qualifiers are appended, are some additional tokens that are appended to the board name to create a board target. And here we have an example with West build. You can see how the format of the target looks like. It has a board name, starts with a board name, then with a board revision. Usually you don't have the board revision. That's mostly optional. And then you have the board qualifier parts that selects you the SoC, the CPU cluster, and sometimes you can have multiple variants for clusters, right? Like it's SMP or not SMP. So this is the short description of some terminology that we'll be using from now on. Now, let's go to this picture, which, by the way, the documentation from Zephyr is very, very good. Very good. This is a picture that I've taken from the documentation folder with some modification because I think it needs some of the adaptation to explain better the version 2 of the hardware. So as we said, Zephyr models the hardware as layers which build one on top of the other. And we start with the architecture and CPUs types, and then we get into a part that's related to SoC. And we split this into a SoC family. A SoC family is usually a group of related chips from a vendor. And then a particular instance of a SoC family, it's called a series. And then inside that instance, we can have actual SoCs, right? This is sometimes, and at first, can be confusing when you add support for a new board because you need to understand your hardware and the family of the hardware really well in order to get this correctly. And then on top of that comes the board implementation where you actually select the SoC and additional devices that you want to enable. Now let's have this instance with the NXP family. Sometimes naming can be confusing, but we shouldn't get lost into these details. After some iteration, you will learn by heart this. As for the architecture, on our hardware that we want to implement, the 8MPFVK, you see we have 3 types of architecture here: ARM64, ARM, and Extensa LX6. Then as for the CPU types, we have A53, M7, and Hi-Fi 4 DSP. Luckily, when you add support for a new board, all of these 2 layers are already there. Support for this are already there for you. Now it comes the part that you need to actually do, is to identify the family, series, and SoC. And this everything comes into Zephyr hierarchy in the SoC vendor, SoC family directory. And then on top of that, you add the board implementation, which usually comes in board, vendor, board name. Now this board name should be unique because they are directory inside the vendor directory. There is a West boards option that lists all the existing boards in Zephyr, and you can get some inspiration from there, but you shouldn't add a name that's already there. Now, let's actually start doing the implementation, and the first thing we want to add is the, inside the SoC vendor, we need to look at the SOC YAML file. That basically describes how your SOC looks like in the Zephyr model. And we have the family, it's for NXP is named NXP I.MX, the series is 8M, and the SOC name is this name that doesn't make any sense at first, but you need to look in the data sheet and take this SoC name from there. And then we define the clusters. Clusters can contain CPUs of the same type. And we have here multiple clusters for different types of the CPU, and we have ADSP, A53, and M7. Now, we'll have a look at the family. As I said, the family is a group of related chips from a vendor that shares some similarities, like features, architecture, design principles. The implementation files can be found in SoC vendor SOC family, and here we have some families from NXP, like the I.MX, RT, and S32, and also look at our neighbors, Intel and Nordic, they have some families there. Now we go and look at the series. So inside the family, we can have multiple related SoCs, and the families here for an I.MX can be 8M, 8ULP, the new 9 family, right? And you can see here we have a bunch of CMake lists, kconfig files. We will discuss about important ones later. But most of these kconfig just help you to reach to the next level. Basically, they are including all the kconfigs from the subdirectories that are below them. It's not nothing complex here with these kconfigs. Now, let's have short navigation through these kconfigs. As I said, we start with this kconfig SoC, and what basically this entire hierarchy of kconfig is allow you to select each layer. So we start with the ADSP layer at line 12, which basically selects the SoC that we are using. And then if we go at line 8, we are selecting the series. And so on, going to the first line, we are selecting the family. The only thing missing here is how do we actually select the ADSP one at line 12. So we are now in the SoC area, and that config is selected from the board part. Right? And we'll see later actually how this is selected. Now, what is a board? We've already discussed a little bit about it. A board is the target hardware we want to build an application for. And the important thing here and the nicer thing is that this hardware model actually decouples the hardware from the application that's running on it. And the abstractization is done by the board. The hardware is implemented until board, and then applications are built on top of the board and can enhance and add overlays on top of the board. Now, all the boards are in the Zephyr boards vendor name. That's another enhancement brought by the version 2 model. And this directory contains some important files that we start with, and some of the other files which are optional. The important files are the board YAML, the kconfig with the board name, and the actual device tree for the current target that we are building. If we look on the right side, we see that each target, like A53, ADSP, and M7, has their own YAML file, DTS file, because it's actually different hardware, even if in the same board, and a file named default config, which helps you select some default options, config options. Now let's see what does the board YAML contains. This basically describes the metadata of the board. And we have the board name, it's most important, vendor sometimes, and the SOC. The SOCs are described here. So now you see how we link the board with the actual SOC that it contains by this file. And an important note is that the CPUs are not described here. The clusters are not described here because the clusters are contained by the actual SOC, and that's the way we bring in the exact clusters. Another important thing is that you may have multiple boards defined in the same board directory. Let's not get into that detail because now we are in the level we want to implement something that's very simple and very easy for us. One of the things that's also borrowed from the Linux kernel is the description of the hardware, which is done via the device tree. One surprise for me was that the device tree are not actually working as in the Linux kernel, where the device trees and the hardware description is parsed at boot time, and the hardware is actually discovered at boot time. With Zephyr, the hardware and the device trees are parsed at compile time, and everything is already there when you have the image. Now, our goal was to add support for a minimal SoC that can run the hello world. So what we actually need is to add the description for the CPUs, and we have here the CPUs from Tensilica. And then we need the basically the serial console, the UART, and things that make the UART work, like the pin control and the clocks that are described on the right side. And once you have this device tree, this helps compiles and select you at compile time the hardware that you actually have. And now this is the final piece of the puzzle for the board, is how we actually get everything started. How do you actually, what's the entry point that selects everything on the compilation side? And that's the target name that's passed to the west command. And you can see here, we have the target name is i.mxmp.avk, that's the board name. And then are the qualifiers, the SOCs and the CPU cluster. And of course, at the end, it's the hello world part. Now, once you pass this name to the west build, there are some magic happening inside the CMake files. This magic, what actually does, it sets some variables with the names that it can infer from the input of west command. So here from the input of the west command, it can create the variable which is named on line 3 in the image below, which is named I.mx8 ML8 ADSP. And if you look at the parameter of west, of -b parameter, it's exactly the name of this variable. And this variable will select the ADSP1. And if we go back to the sock directory, we see that this actual ADSP config was the one that started everything, right? And once we do this, we have the actual firmware image that we can load. And we can do the same for the other CPU clusters, like for the M7 and for the ADSP. Now, usually, what we also need here is some tools that help you load the image and boot code or something like that. But the nicer thing that we've encountered with this Hi-Fi 4 is that we load the, the image from the Linux kernel side. So we don't have to deal with this on the Zephyr side. We just, Linux puts the image somewhere in a memory and just press start button. And at that point, the Hi-Fi 4 starts running and initializes devices and calls into the main function of your application, which in our case is the Hello World one, which prints Hello World. Now, that's the basic steps that you need to do for a simple implementation. Of course, for more complex stuff, you will need to add more drivers and more drivers for your devices that can do the work that you need to do. Now, let's see, we have the code. Let's see how can we get it upstream. First thing, and I was very surprised because when I started working, I just jumped into the code and jumped into the process. I didn't read the documentation. But my advice is start reading the documentation because for Zephyr is actually pretty good. And there are guidelines for basically everything you need to know. Sometimes there might be some boring reading because there are a lot of things to read, but you can find the answer to almost all your questions. And also, for the community, there is a Discord channel where actually everything you can think of has a sub-channel. And it's harder to find the sub-channel than to actually find the answer for your question. So there are guidelines for the contributions, for coding, for another trick that you can do is that when you don't know exactly how to write the code and you just have an idea, you send a request for comments. And then others will help you write the code. And then there is also a documentation for how to write documentation, which is awesome. Now, let's have a look on how you actually start. If you're the first time when you're contributing, I think the best way is to find a small issue or a small bug that you can send and just to get familiar with the entire process. The compilation of the code, the sending of the pull request. And one good place to start is in the issue tab in GitHub, there is a label named good first issue. Then you also need to read the coding style document, which is similar with the Linux kernel one. And it has a similar tool for checking if the coding style is compliant. This is named checkpatch.pl, and you can, you should run it every time you send the code. Now, another important message, and no one tells you, is that in order to get your patch accepted faster, you need to make the reviewer's life easy. So one of the things is to write a good commit message. And Another trick that you can do is to look in the Git history around that area that you are adding code, how others wrote the commit messages and get some inspiration from there. Right? So once you have everything, you can start the creation of the pull request. From my experience, the pull request shouldn't contain more than 5 patches. When it contains more than 5 patches, it means that there's a lot of mental effort for the reviewers to go through all of your patches. So better split it in up to 5 patches, and each patch should contain a logical change, right? And even, so for example, if you have a complex application that you want to add support with a board, just first add the support for the initial board with hello world, and then on top of that, you may add the drivers in another pull request, and on top of that, you can actually add your application, right? This helps the reviewer and helps you gain trust, that community gains trust, and that you are following the rules. Now, another thing up here, you send the pull requester, the pull request, just follow for the updates and answer to the comments. Don't just ignore some of them. If you don't agree with some of the content, you even can discuss with the reviewer on Discord or have the communication on GitHub, but never leave anything that's not resolved until you send the next iteration of the patches. And another thing that I do once I submit the next version is I write a small change log so that the reviewer can remember what happened 2 weeks ago, or when's the next iteration of that. Right, so this is how a simple pull request looks like. For the initial support for ADSP, it just has 2 patches, one that introduces the initial SoC support and the other one that adds the board support. And that's all for now. After you send the pull request, just be patient. Sometimes maintainers are busy, sometimes they delay your pull request because they have other things more important. Now, the general rule is that the assignee from GitHub should review your code or should give you approved, and you should find another one, so you should have at least 2 reviewed bys. Right? Now, as some generic conduct that could work is that after 1 week of inactivity, you can ping the assignee or you can tag them on GitHub. And after another week, you can look on the PR help sub-channel on Discord and ask for help there. There is also a page, but I think this is mostly for maintainers, which they can see the status of the page, of the pull request, and there is a rule that at least 2 days should pass until the pull request get merged. With this time, people can, CI can run, people can have time to look at it. But this happens and works for trivial pull requests. For more complex pull requests, even if this is only the initial support, you should expect around 2 weeks until your change gets merged. So the rule is that you need to be patient. Right? Now, let's see some final thoughts and a sketch of a timeline. If you need to add the toolchain support, then your plans will be delayed a little bit. Your pull request will be delayed by the how fast the new release of the Zephyr SDK is released. So you should budget for this at least 1 month. At least 1 month, but in this 1 month you can start working on the actual board support and you can interact with the maintainers, but the pull request won't be accepted once the CI compiles your code and eventually runs on small tests. All right, so you should expect around 4 weeks for this, and then 1 week for CI integration, because it's not that easy. You need to modify some file in CIs, and then you need to make sure that nothing breaks because there is a new version of the SDK. And around the fifth week, you can expect some of your pull requests to get merged. And then you add the drivers, and then you add the other things that you need to add there. So basically, this is my experience with Zephyr community. It's a very welcoming community, and people are willing to help you. But this also means that you need to address the comments every time and do your work, right? So if you have any questions, or feel free to get in touch on my email. Thank you. We still have around 4 minutes. You can try this one.
Speak loudly then.
Ah, okay.
I was going to bring a mic, but the mic's not working.
I have another one here. You can try this one. I'm not sure how to turn it on, but. Oh.
Hello.
Yeah, it works.
Okay. I was just wondering if you're going to add any more boards, support other boards to
Yeah.
Zephyr.
Yep,
You're
yep.
planning to?
Definitely, yeah. This is only, we've seen here the Hi-Fi 4 on 8MP AVK. I'm having a pull request in review for the iDynamics RT685.
Okay.
And we already have support for all the boards that have a DSP from MPU families of NXP.
Cool. Okay.
Right.
That's all I wanted to know.
Yeah,
Thank you.
thank you.
Anybody else?
A very simple question. What's the like Git workflow that's involved with Zephyr? Like you have the option to like rebase the commits that you've made. You can merge them. You know, what's standard when you're actually contributing?
Yeah, standard is start from main branch, create your branch where you add the changes, then you push the changes on your fork of the repo, and from there you create a pull request. Next time, when you add modification, if you're in luck, then your pull request will get merged, and that's done for you. Next time when you add modification, you just rebase your changes and force push them on your repo, and the pull request will be automatically updated. This is the basic Git flow that GitHub allows.
Well, so I guess what I'm asking is, should I be careful and make sure that my individual commits that are as part of the pull request are like individually acceptable,
Yes.
Individually buildable,
Yes.
you know,
Yes,
functional all independently?
That's a hard yes.
Okay. Thank you.
It will check each commit.
Yeah.
Yeah, this Zephyr project's one of their big driving factors is to have a very clean history,
Yeah.
very clean, so that you'll
If you
have
could-
reviewers that will look at your commit history to make sure that it makes sense, which is what he was saying before.
And because you don't want to break the bisectability, right?
Yeah, bisectability.
Bisectability. Once you have a problem, this can save you. And once you have a problem and you see that one commit doesn't compile, then you will be very upset.
Follow up then, so you mentioned that the CI runs against each individual commit that's part of a pull request.
Yeah.
What other CI is there? Like what checks is it actually performing when it's running it?
So there is some basic compilation. There is some basic static checkers like check patch. I'm not sure if we have more complex checks. We have git lint, which checks that your commit follows some rules, like it has some prefix with the area of the commit. It does actually has some messaging. You cannot just submit empty commits, and some basic stuff. And then we have a set of tests that run. I'm not sure if they are run actually on the hardware or only we have QEMU-based tests there.
Okay. If there's no other questions, then thank you very much.
Thank you.